I hate the definition from Kopp et al. I hate it. You know that he's an S3 employee? Yeah? No? You know him? Steve Kopp. I once had a dinner with him and I told him in the end, you guys are just drug dealers. That was the last time I talked to an S3 person. Oh, that's not true. I occasionally talk to my group, but he has several hats. Steve. Well, he was going like, oh, but open source and so on. You know, if I have hydrologists who want to know the details of this and this special module, then I give it to them. You know, if they want to see it, I give it to them. I was doing fuck you with your give it to them stuff. But you can't share your screen. Somebody has to make you host.
Yeah, sorry. Yeah, I didn't have the SD card for the camera, so I got to get it. Okay.
Yeah, okay. And so here you will use a kind of virtual environment to compute, very limited with a low amount of RAM, low amount of CPU, but I tested several times and you can actually reproduce all these steps that I will present here. And yes, so let's, one thing that is really important, so because when you open this link, it's basically like a link for my computation notebook. So you will not really be able to edit and do any kind of modifications, even like executing. So I recommend to it's like to really execute the computation notebook. You need to save a copy in your Google Drive. So when you do like this, I will just click here. So you can actually have a copy, and I will also use this copy. So I will keep untouched the original version linked there. And in this copy, you have full flexibility. So let's start. Basically, I prepared a few slides for this session, but after I decided to just incorporate everything in one computation notebook, putting some figures and things like that. So before to really enter in the code, I believe that it's really important to make some definitions and provide a conceptual background for what we are doing here. So basically, I will talk about the definitions and a few examples of Raster data cubes. After that, I will talk about cloud optimized GeoTIFF, what are the key aspects of this format. And later, after the cloud optimized GeoTIFF, I will enter in the spatial temporal asset catalogs. So what is this not format, but kind of definition of APIs, and we have several implementations also. And lastly, what are the most common geospatial libraries in the Python environment? So, and I have like a kind of software stack to try to explain how these libraries integrate with each other. So yeah, let's start with the raster data cube. So basically I have two definitions here, one more generic just for data cubes, not raster data cube. And the second definition is actually provided by Mario Zato and Edzer. But the first definition is really generic. I know there is no consensus about it, and you have other definitions also, but just to have ideas. So it's data cube, it's basically a generic term used to describe an array of multiple dimensions. So I think the core concept of a data cube is the possibility to have multiple dimensions. Of course, in the context of Earth observation data, geospatial data, we are interested in very specific dimensions, but on a data perspective, it would be possible to have multiple dimensions. So, and if you think about data cube, should help like organize data, simplifying data management, and improve the performance for query analysis. So it also infers like very specific ways to organize the data, but also make it available through different APIs and platforms. So in a more specific geospatial context, so a regular dense and raster data cube, it's actually 4 dimensions array with longitude, latitude, time, and bands. So if you think in a, for example, a Landsat data or Sentinel, like really satellite data, you kind of have all these 4 dimensions, like 2 dimensions to represent the space, 1 dimension representing the time, and 4 dimension representing the spectral bands, blue, green, red, and near. And there are some specific properties. So the spatial dimension needs to refer to a single spatial reference system. So we need to have like a constant spatial size for the cells, and you can define the offset and the cells for all the data cube. And other important aspect, you have like a constant temporal duration. So you could have a data cube on a daily basis, or you can have a data cube on a monthly basis. So not kind of irregular temporal duration. And so the temporal reference, it's simple, defined by a start, date time, and these temporal durations in cells. And for every combination of these dimensions, you will end up with a single scalar attribute, as there is here to provide more information if I miss it some aspect. But basically, this is for me, it's like the concept that the definition that we can use to really start working with database. But also in this paper, there is a very important claim that if you build a data cube, basically you can think of like building a data cube like a conversion of an image collection, like several images, like organized in different ways, maybe with different pixel size over different resolutions and things like that. And you can like really align them, warp everything, creating like a homogeneous structure, as we are seeing here in this picture. But when you build the data cube, it can include like information loss. So basically, the way that you can aggregate, for example, temporal data, or you need maybe to do a kind of reprojection for a very specific, for a different projection system and things like that. But the main point here is this process needs to consider the user definitions and the restrictions and for your application. So that's why, for example, you might have like different data cubes, and there are some software solutions that can help with that, to like this conversion from an image collection to a data cube. So GDAL cubes sits both in R and Force, that is also like implements a kind of spectral harmonization for Landsat and Sentinel. So basically you have the software, and the users can use the software to build their own data cubes. So, but if you think about it, it's kind of like a lot of work, and maybe it will require a lot of computing also. So you have several, not several, but you have multiple examples of data cube, and here I'm putting like data for initiatives that actually provide the data, and maybe they have some like internal platform to access it, but there is no kind of like open platform to access and interact with the data. And and what I'm referring here as platform, it's actually like the kind of cloud platform that you could access to interact and retrieve data from this data cube. So, and I think when we refer to data cube, we actually refer at the same time of data and platform. So I agree. I think that it might be a mismatch here. And from my perspective, I prefer to think in a data cube as a data structure, like data that you can access. Of course, you need a platform to that, but with these new cloud native formats, you can actually have data and client accessing directly the data without any middleware, without any software component between it. So, for example, now we have probably everybody here already listened about the Google Earth Engine. So we have the Google Earth Engine. It's an awesome platform, and of course, internally they have a kind of data cube to put all these collections that are available in the platform in a very structured way. But what the users can access, it's actually the platform and use their infrastructure. But if you think about just accessing the data, you can actually use, for example, cloud optimized duties, ZARs, TileDB to really access directly the data without any kind of platform to do this, to intermediate it for you. It's exactly what I will show here for a very limited context, but you could have it running, for example, in Amazon, and to access this data, for example, and build your like a data cube there. But I think the most important here is actually this concept to use these cloud native formats and client accessing directly it without any software component in between. So basically, we will use the Open Environmental Data Cube. If you click here, you can see a kind of, this is a stack browser interface. So we are using a stack protocol here to make available all these data sets. I will explain in detail how it is structured. But basically here, it's just like an interface, but when you access this data, you actually access a cloud-optimized GeoTIFF hosted in the cloud. So let's go to the next section. And so, yeah, the next section, considering this definition, the appearance of these new cloud-native formats, I would say that cloud-optimized GeoTIFF, it's really a very robust format, and we mostly work with that at OpenGeoHub. And I can explain that there are three key aspects that makes cloud-optimized GeoTIFF really powerful for geospatial applications in general. So, and you have the three aspects here. So first, you have this lossless compression. It's not something that is specifically for the cloud-optimized GeoTIFF. You already have it in the TIFF format, but it's a way to compress the data, to save it in a storage media like a hard drive, and decompress the data, recovering and restoring the data to the original format. So you can have like a matrix representation in memory. And when you save it, you basically compress, you reduce the size of the file, and you can decompress it and have exactly the same values. We don't want to lose any bit of information when we are working with geospatial data. But we also have the tiling and the overviews. And when I mean tiling, it's exactly what we are seeing, that pyramid figure. So basically you have, you could have a big raster image with several columns and rows. And one nice way to save and store it in the disk, it's actually split this big image in really small cells and small grids, for example, of 256 by 256 pixels. And when you actually split it in these small chunks, it means that you will save in the hard drive all this data really close each other. So what means that if you have a big image, but you want to really access, I don't know, a very specific region of this image, not the whole image, but just a portion of the data, you don't need to read all the image from the disk. And it improves a lot this access to small parts of the raster data. But you also have this functionality available, overviews, that it's basically a pre-computed coarse resolution representation in different levels of this big matrix. So, for example, it means that no matter the size of your raster data, you can always pre-compute it and create like coarse resolutions. And the official implementation of the cloud-optimized GeoTIFF in GDAL, I think it's 8 levels. So it means that in the level 1, you can see the whole picture, the big picture of the raster data. So for example, in this case, you can actually see, for example, here, if you enter in the continental Europe landmass, you can see a thumbnail here that it will show the whole Europe. So where is the thumbnail? Yes, this. So you can see this. So this is a 30-meter image for the Europe, but of course, to load it you don't need to, you could load all the data, but you can also pre-compute and have like a coarse resolution, maybe, I don't know, 5 kilometer representation of this data to visualize it. And when you zoom in different parts of Europe, you can just, actually the drive do this work for you. You can change from one level to another. So it's just a visualization, it's just a functionality to improve the visualization, but it's very important for who works with geospatial data. And so considering this, all these functionalities, styling, overviews, lossless compression, all these basically 3 functionalities, they were available in the GeoTIFF. But when you, what really improved and make it cloud optimized GeoTIFF available, it's actually the HTTP GET range requests. It means that if you have a file hosted in a HTTP server, in a cloud, in a link remotely, you can actually request remotely just a chunk, a portion of the data. And it allows you to make random access to all these structures. So you can make random access to the level 1 and retrieve, for example, the whole Europe, or you can make random access to a very specific area. I don't know, considering the whole Europe, if we zoom in Siegburg, for example, it will just read that very specific part of the data, considering these HTTP GET range requests. And for me, one of the best ways to really host the cloud optimized GeoTIFF, it's in the as object storage. So object storage, it's a different kind of paradigm to host data. So instead to have like a file storage or a hierarchical structure to organize the data, you can have like a unique identifier for a chunk of data, no matter what is it, could be text, media, or raster data, as in our case, and you can have a metadata. So with this unique identifier, it's a kind of like unique URL to access the data through the whole internet, and it allows you to really take advantage of all that functionalities. So I will just as example, so I will copy this URL here, copy link, and I will open this in the QuantGIS, and you can do it with any layer that this is just like a plugin problem. You can do it with any layer available as cloud optimized GeoTIFF in the Echo Data Cube. So if you go to add layer, raster layer, here you have this option to insert a HTTP URL. And here we go. So this is actually the landmask that we use it to define all the layers from the Echo Data Cube. And you can actually zoom in here and you will see like almost instantaneously the data. And this is remote data. So this is what I was talking in the beginning. So the QuantGIS here is the client. The data is hosted in a cloud object service solution. We use it Wasabi here, compatible with the S3 protocol, but you have full flexibility. So it's the same thing to access a GeoTIFF locally, but everything is seamless, and you just request the portion of the data that you need. So if you probably, in this case here, we will access level 2 or level 1. So it's a small image, not the 30-meter resolution. So all these mechanisms, all these functionalities integrated and working together, for me, that's the cloud optimized GeoTIFF, not the definition, but the main advantage to use this format. So it's not pure format, but the whole possibility that you can have using it. And okay, but if we start just hosting these cloud optimized GeoTIFF files in the cloud, we need to have an index. We need to find like, okay, how I can look, how I can search for raster data, considering these new cloud native formats. And so here we can enter with the spatial temporal asset catalogs. So basically, you can think this as like a catalog that hosts what they call the spatial temporal asset. So basically, it's a file that represents information about Earth captured in certain space and time. So you can have like multiple assets organized in a very nice API specification with like endpoints and predefined JSON formats and pretty extensible. So you can add new extensions to, for example, cover, I don't know, LiDAR data. So it's not just specific for image, but for cloud points, data cubes, full module video, and things like that. So basically here you have mainly 4 entities, I would say. So you have a catalog. The catalog, it's composed by items and collections. And inside a collection, you can have another stack item, but inside of one item, you need to have an asset. And the asset, it's actually the link to the actual data. But for all these levels, you have different metadata properties like the time, space coverage, description, title, and things like that. So you can have 2 implementations of the stack catalog. You could have a static catalog or a dynamic catalog. So I will not enter too much in detail here. You have a few implementations for a dynamic catalog, but what it's matter is the catalog that we will access in this tutorial. It's basically a static catalog. So it's the same approach that we are providing for the cloud optimized GeoTips. It's just several JSON files hosted in the cloud as a cloud object in a cloud object service. So, and before to explain about the Python stack, software stack, I will just, first I will clean all the outputs, and I will execute this. And so I recommend the same to you because it will take a while to download all the dependencies and create the execution kernel. So now I will back here. So basically, we have multiple kind of APIs in for Python and libraries, but here we don't have only like geospatial focused libraries and packages. So here I inserted the most part of the packages and libraries that I use, and you don't need to know all these packages to really start. But I think the key message here, you have some fundamental libraries like GDAL, Geos, and Proj that are implemented in C, C++, and you need to really pay attention in the way that it relates with, for example, all these APIs in Python. And my suggestion is the easiest way to really manage these dependencies is using Conda. So basically, it creates a kind of isolated environment for the users. And download the specific libraries of GDALs, Geos, Proj, and other native and C++ libraries, matching exactly the same version that you need to run. So, for example, you might have like a Raster.io version that it's not, for example, compatible with your current GDAL because maybe your GDAL library is old. So this is, I think, the key point here. And personally, I use mostly Raster.io and GeoPandas. We had a very nice overview of GeoPandas with Martin this morning. And with both, so Raster.io, I used to do basically to read the raster data and convert it to a NumPy, that it's basically a matrix representation of an image in Python. And GeoPandas, it's a way to interact and read vector data. So from this side here, we have like general and data science libraries. So we have SciPy that implements some fancy modeling approach. Stats model that implements some, it's really close to what we have for regressions, for example, in R. The scikit-learn, the basic library to do machine learning with several algorithms implemented. And I mostly use JupyterLab to really have a bit more functionality. It's similar to what you have with RStudio. And we develop internally in the context of the EcoData Cube, a library called EUMap, that it's basically a wrapper for several functions that we have. So for example, with Raster.io, to read, for example, multiple rasters and stack them and create one single data cube representation using NumPy, we basically created a wrapper function called read rasters, where you can just pass, for example, like a list of URLs, read it, and you can even restrict for a specific area. We will show it here. I will show it here. And you can just have like a ready-to-use representation of NumPy array to do whatever you want. So I will work with some of these functions implemented in EUMap. And the IPy leaflet, it's just a way to open a kind of web GIS inside of, it's not really a web GIS, it's more like, it's similar to what we have with leaflet, but it's just a way to navigate and have an interactive map inside of Python. Here we have a short description for every library, so it might be helpful for really understands most part of this library. So the basic library that we are installing here, it's the IPy leaflet, PyArrow to read the Parquet files, and the EUMap. And as we are working in the Colab, so as I mentioned, we have several like problems related with this dependency with C and C++, because it's basically, it's a tricky problem. So here I created a specific branch that it works with Colab. So this instruction here, it's slightly different from this one because it's just install the dependencies without breaking the environment here in the Colab, because they use the old version of GDAO, and we will not use any kind of the new functionalities provided by GDAO in this tutorial. So basically, when you execute this first line, it's installing like several packages and library, and it will request to restart the runtime, and you can do it. And again, this is a very specific issue of the Colab. So they have a kind of old version, and I think they use Ubuntu, I'm not sure. And you need to set up these certificates, authority files to allow, for example, the Raster.io to access remote files, as we will do. So basically, you just need to execute these two functions to set up it in the your environment. And one last thing, so if you open the EUMap here, EUMap, it's not here, I will add later, but if you open the EUMap homepage, there are some instructions here to install through Conda. You can use the same environment to replicate all the libraries, but you can also use the Jupyter, our Docker container with Jupyter Notebook and several libraries organized. We also have one for R, with RStudio and Grass and Saga. So basically, we do it to do our daily work. And okay, let's move forward. And so I already talked about it, but I will execute this. And basically here, we are accessing the training data provided to the hackathon. So basically, it's a Parquet format. We will have a GeoParquet session after this one. and to explain more about this format. But for now, you just need to know that it's a cloud native data format, more specifically for tabular data. And here, the way that it's structured here, it's the same way that I talked about the cloud optimized geotip. So basically, you have a URL to access this file, but in some case, you don't want to load the whole file. So with Parquet, you can have just like a kind of the metadata, just a red retriever to access, for example, how many columns you have, or you can actually see what are the columns available. And here actually it's executing everything again, but you can see all the columns and formats and things like that. So this is basically the hackathon data with several covariates that we already overlaid and provided in the for the participants of the hackathon. And basically what we will do here, I will show how we did this overlay. So how we took the pixels that you have in each of these columns. Of course, I will do with a small data set and way less columns, but the concept is the same one. With one difference, that we will access the catalog to actually retrieve, like, if what are the data, what are the cloud optimized geotips that should be used to do this operation. So let's use what Parquet can offer to us and basically read just the columns related to the samples. So here are the columns that I want to read. I basically am removing everything related to the overlay, like Landsat data, temperature, modes, and all that, like big columns with big names referring to the raster data and to the data set. And here I'm basically passing these columns of interest, reading just it, and converting to a pandas data frame. And here we go. So this is what we have, 8 columns, 1,552 rows. And let's do some analysis and see, for example, how many points we have per each year. So yes, we have 3 years here. So you can see I'm doing like I'm taking advantage of what pandas can offer. So basically I'm counting the values of the year and doing a plot with in horizontal bar, just to see like how many records we have for each year. And I can do the same for area, and also I can do the same for label. So here we have much more data for Brazil, and we also have much more data for the others, the class others. So, but as I said, we want to overlay the samples with the Echo Data Cube. It's basically a data cube just for Europe. So the Brazilian points here will not be very useful. So what we will do now, it's basically restrict the points to Europe. And as we can see here, there is this imbalance between the class. And for now, because I will restrict a lot the number of points, for now I will just aggregate what is grass. So basically seeded grass and natural and semi-natural grass. I will aggregate to a single class like pasture. And that's what I'm doing here. So basically what is 1 will be 1, what is 2, it will be 1, and 3 will be 2. So this is just a map that will replace all the class to 1, or the value 1 or the value 2. And I will do the same for the class label. And after that, we can check how many samples we have for the aggregated class. And yes, here we go. So basically we have about a bit more of 300 samples. And these, of course, these samples, they have the overlay the latitude and the longitude information, and we will use it to do the overlay. Okay, so now we have the samples ready to go. So one way to do it is actually go to that website and, I don't know, try to find what are the layers that might interest in you and things like that. So, and of course, it's not very efficient. This browser, it's more to provide an overview. And the main advantage of Stack, it's actually you can interact with the API through code. So here we are using the PyStack. It's kind of the official implementation of the stack for Python, and you have other implementations also available. And here it's the URL of our catalog. As I said, it's a static catalog. So basically, it's not like a software that it's running. It's just like several JSON files that are hosted in a cloud object service. And you can retrieve this URL if you go here on top and get it from source. So basically, you can retrieve what is the URL used to produce this stack browser. Okay, let's do it. And you can see that I'm calling a method from file, but this is a remote file. So it works in the same way. Okay, and this, it's basically, as I explained, a static catalog. So there is no easy way to like implement search functions. So we are working internally to transform it in a dynamic catalog. Probably we will use the front-end solution. It's a way to really mirror all these, all the collections that we have for a dynamic implementation. And after that, we will have the search endpoint. But for now, we don't have it. So what we will do, basically, I will create like a method here. I will not explain all the steps of this method, but it's basically a way to iterate over the catalog for each collection and retrieve what are the assets. And the asset, it's the last step here when you have this collection get assets. And I can match, for example, this and really have the assets that are related with GeoTIFF or cloud optimized GeoTIFF. So I'm just interested here in GeoTIFFs and mostly cloud optimized GeoTIFFs. And later I'm just creating like a nice and clean representation of the result in a data frame. So it will allow me to really do searches and do some operations. So basically, what we did to interact with the catalog, it's a stack index. So there is a class implemented in the EUMap package that access the catalog and create a kind of local index based in this wash carry. Actually, the framework it's wash, but it allows us to do like full and free search based like in text. Considering like a local index. So here, it's just, as I said, most of what we have in UMap, it's a wrapper for other libraries in Python, but here it's a wrapper to do an index for all the collections that we have available in the catalog. So when you execute it, it will start and it will take a while, maybe 2 minutes, to produce like a local index with all the 146 collections that we have available in the Echo Data Cube. So the first is running this, so it's creating an index, and later I'm doing a carry here that I want to quarterly, SWOR1, and Landsat. I'm carrying like this in this index. If we had a dynamic catalog, I could execute it in the endpoint and just retrieve what we have for this carry, and I will receive all the collections that are that match with this carry here. So, and here I will receive like in this case it's just one collection, but you can, for example, do like this, and I will not execute it, but you can do like this, so you will receive like two collections, SWOR1 and SWOR2. But for sake of simplicity here, we will just use one band to do the overlay. And we are working with the Sentinel-1. So basically it's still doing the local index. And when it finishes, we will see a folder here called the stack index. And with the result, so the result of this query is basically ID and a title. So the ID of the collection, it's just, for example, when you enter here, you can have like in the URL, you can have this, and basically this is the ID of the collection. And so yes, the index finished. So we have 146 collection, and now it's reading all the cloud optimized geotips available in this collection: quarterly, SWOR1 band of Gladland SAT R&D 2000-2020. So it takes some time because it's entered in every GeoJSON record of this collection and really access what is the URL to retrieve the cloud optimized geotip. Again, this is something that we are doing just because it's a static catalog. If it's for example a dynamic catalog, that all this processing would be executed in the server side, and you just retrieve, we could retrieve just like, for example, the items of interest. And in the end, it's just aggregating it, and it will return and show to us like a GeoPandas data frame representation. So here we have 336 cloud optimized geotiff files. You have the URL here, and the method that we defined basically provides the year, the start and the end date of each file, the name of the asset, and the name of the collection. So you have basically all the information that you need to interact with that. And it's just like I'm just creating it like this, so you could add more or remove some of the features of the values in the data frame structure. So, okay, now we have it, but again, it's a lot of data, and this is actually a time series if you analyze it. So, but also like for this time series, we also have like multiple bands. So for example, if we go back here, you can probably navigate and find this. So this is the Landsat data that we have. Okay, so we have now a data frame representation of all these files available here, but I will just enter in one here, 2000. But for every, like this is an item and this is a collection. So the first one, it's a collection. I entered in an item, and so a collection has several items, but inside of an item, I have several assets. And for this specific case, it means that we took, for example, all the Landsat data available from June to September, so 25 of June, 12 of September. We removed all the clouds, we aggregated and created a temporal composite. We did a gap filling, so that's why you can see like a full picture without gaps. But for this approach, of course, we had like pixel with 2, 3 observations, maybe pixel with 5 observations. So to not like really lose any information, not any information, we lost some information here. We calculated the 3 percentiles with the remaining values. So it means that for this time frame, 3 months of Landsat data, we have a kind of, we have a way to capture the seasonality. So percentile 25, 50, and 75. Of course, if you have just 1 pixel, and luckily you have like 1 pixel, because in some cases we have like only gaps, you will have the same value for all the percentiles. But this is a kind of property of the data and the method that we are applying here. And as I said in the first day, this might not be useful for all the applications. So maybe our gap filling approach could introduce some problems for example, detect deforestation. So that's why we have the quality assessment flag. So basically this layer, it's providing where we did the gap filling and where we didn't implement the gap filling. So it's basically real data. So this is a very important aspect. And if you think about the way that these cloud optimized geotiffs are organized in this stack, I would say that it's a data cube, but not like in the same chunk, in the same structure, or in a single file as we tend to think. So it's a data cube because we did several pre-processing. We organized all this data considering the same resolution, the same bounding box, and we matched everything. We removed the clouds. We are providing metadata per pixel, and you can access it for any part of Europe to do one, for example, further processing. But again, you need to be aware that it's could be not the right data for your application. So that's why we are also providing this metadata per pixel. Okay, so, but for this exercise, we will use just the percentile 50. So that's why I created a pandas data frame, so I can just use the string operator and check if it contains just the SWOR 1 P50. And I'm only interested here in this case in the URLs to see. And if I do it, I have 84 URLs. So it means that, and if you print this URL, you can see that it's sorted because I think the method already implemented it. So you have like a sequential of, it's actually a time series of URLs. So, okay, let's stick with this number and see what is the max year. So yeah, the most recent year that we have is 2020. And to really start doing the overlay, let's restrict for the 2020, but I will explain something later before the overlay. So we can see that some of, like the first URL, it's actually like what we call like it's a season proxy for the winter, because the seasons might change year to year. So this is just a calendar date that we tried to match with the seasons. But you can see that actually starts in December 2019. So, but the date that the reference date that we are using to do this analysis is actually the end date. So everything is in 2020. But if we go back here, we can see that. See if I can. So I can see that actually I have samples from multiple years, right? Most part of my samples are in 2020, but I have also samples for 2019 and 2018. And so what I need to do to actually perform a space-time overlay, it's actually match for all these samples. I need to match the year of the sample, like this, the reference date for the sample with the Landsat date. So I will end up with a data frame, with a table, with values, for example, for these 4 bands, that for matching exactly in that time frame. So, and to do it, basically we call this operation a space-time overlay that matches on a yearly base. You can match in different time frames. You could match, I don't know, in a monthly time frame. But in the way that we implemented, because it was really implemented to do modeling, like with long time series, not really long, but 20 years time series, we just support the yearly temporal match. So, and I will show how to do it. So, but first, we need to convert the samples. As I said, it's a Parquet format. We read and we have a data frame, but we need to convert it for a geodata frame. So to actually have the location of the samples and as point coordinates. And when I do it, basically I have the longitude and latitude, and the provided longitude and latitude, it's in this projection system, so very standard. But the images that we are accessing, the Echo Data Cube, they are in a different projection. So we are using a European projection. I think it's 35, something like that, the EPSG code. And basically, this operation here, it's just like a way to access the projection system and do the conversion, and ending up with a point in the right projection system to do the overlay. Other important thing, remember, you don't have any data in this platform. Everything here it's accessing directly to cloud. So the stack and even like the URL of Parquet, they work here in this context as a database, like a remote database. So you don't know in advance what is the projection system. So that's why we are using Raster.io directly to open the raster URL. I'm just interested in the first one because this is a data cube. So we have the same projection system for all the layers. And for this data source, I'm just retrieving the projection system that it's defined. So this is not actually reading the data, reading the image, it's just like retrieving the metadata. And that's, for example, one of the advantages of the things that I explained, the concepts that I explained in the beginning. So it's a way to access just a portion of the metadata. This is like a random access, like a range access in the whole file that works remotely. So this is something that really allows us to really access the data in this way. Okay, but if you do the overlay in the way that we show here, it will do the overlay only with the year of 2020. And for some cases, we have timeless layers. So for example, BTM, we don't have a time series of BTM. So it doesn't matter the year. We will just use that sample and get what is the elevation data for this sample. But for the Landsat, we are interested in the time series. And we want to have multiple values from different times, but organized in the same data structure. So that's why I'm converting here the 2000 for placeholder year. And we also implemented in the EOMap this year -1 and year +1, basically because we had this data with this structure. So, and in the end, we will have like these URLs in these formats. So what means that this URL, of course, now it's not valid, but it's a placeholder. I'm indicating for the library where I want to replace the year defined in each sample. And doing it, I can execute the space-time overlay. So basically, I need to pass as argument the training samples, the column date. One thing that it's important, and I forgot, is instead to pass like a string or a column with the year, we have a column with the year. The API expects actually like a data object. It's better work with the data object because I can retrieve the date for the year from there. So that's why we converted the year column to a data time, a date time type, and we send it for the API. So here we are sending as argument the column date and the layers. So here we have 4 layers that it's performing the overlay, and we are checking the progress here. So basically what is happening internally, so for this data frame, it's basically restricting the points. For example, for 2019, we have 75 points. And using these points, it matches with the pixels of the 2019 Landsat data and aggregate it and go to another year. So basically, and this is working remotely. So we don't have the data again. So for all these points, it's just like an access to a remote file and access only that pixel value and aggregating it in a single structure. Actually, this first part, it's kind of to identify where in the image we have samples. And actually now it's performing the overlay. And we can see here what are the images used, for example, run the overlay for 2019. And so now, of course, if you want to do it for, I don't know, 200,000 points, it will be really slow. This is like we created this solution and we put it available to really starting using and test. But of course, there are some limits and bottlenecks considering the network access. So, for example, when we work with this data, we have an internal infrastructure with all these S3 layers organized internally, and we access and do this operation. But for example, if we had like here, we are using a Wasabi, the Wasabi provider, and we could host also this in the S3, for example, using the Amazon Open Data Initiative, and probably it will be improved, for example, the performance to access the data and to retrieve it. And so there are some limitations, but still we are overlaying more than 300 points and getting exactly the pixel values for all these for all these images. And here it's 4 images actually. And I will show what is the result, because of course, if you just aggregate it in different columns, you will not have like exactly one seamless and integrated structure, because they are not exactly the same file. So the way that we solved it's basically removing the year, because we have a placeholder that indicates, for example, where we have the year data. And if you check here, now we have 15 columns, we have the pixel values available. And the name of the column now it's without the year. So it allows us to aggregate in the single structure, in the single column, pixels from different rasters and integrate it. So, okay, now we are ready to start modeling. And so we did the overlay. We have not a great feature space, but we have 4 variables. And what I will do now is use another EUMap class, the Landmapper. And the Landmapper is we have several parameters. I personally don't like it, and probably I need to do some refactoring here. But basically, it's a wrapper for the scikit-learn that integrates like geospatial data and allow us to do like spatial prediction. So in the end of the tutorial, we will do a spatial prediction for a very small area using this class. So because all these machine learning algorithms, they are implemented in the scikit-learn, but for them, it's you just need to train and predict with a matrix, with an array. So it's just a multi-dimensional representation. What Landmapper does, it's just a wrapper for all these, like to abstract the complexities of the geospatial data. So you can send like a GeoPandas to it, and you need to send, for example, what are the columns that you are interested in. And because the data frame now, we have columns that will not be used by the model and things like that. So it manages everything for you, but most important, it also allows us to predict in raster data. So the predictive method that we will use, it will read the raster data and do the prediction with scikit-learn and save an output file. But of course, we don't want to implement like new stuff that are not compatible with the scikit-learn. So everything that we did in the Landmapper, it's fully compatible with the scikit-learn. So you can use a random forest, a keras classifier, that it's a way to integrate TensorFlow with the scikit-learn. You can use XGBoost and everything that implements an estimator interface. And you can do hyperparameter optimization. You can implement pipelines. you can do whatever you want that it's available in the scikit-learn and just provide as an argument for the Landmapper, and the Landmapper will work. You can do regressions. Here it's a classification problem. So what we will do to illustrate it, it's basically, we will create a random forest classifier, 50 trees, so just to reduce a bit the computation time, but we will implement here a hyperparameter optimization. So basically, we have several hyperparameters that you can use to tune the random forest. And of course, this depends on the algorithm that you use. So if you are using like a like a gradient descendant tree, like implemented by the XGBoost, you need to send other parameters. But here it's the parameter, and this is a range. So for example, for the max depth, that is the max depth of every tree in the forest, and you can put a big range here. So I'm putting 5 and 100. So this is basically the distribution of the values that each of these hyperparameter accepts. And to tune and to do the machine learning part here, we are using a randomized search cross-validation. So basically, for this estimator, random forest, and considering these hyperparameter distributions, it will test 10 random combinations. So we have the distribution, right? We defined the boundaries here. So I cannot have, for example, a max depth with 1,000. If I would like to do it, I just need to change for 1,000. But I have the distribution here. And the randomized search CV will iterate and test 10 combinations. You could test 100, you could test 1,000, but in most part of the case, it's not necessary to test like really several of them. To really optimize your model, you need to work in data preprocessing and organizing the data in a different way, or maybe for some algorithms, the scale of the input variables matters and things like that. So now we define it, 2 objects here, 2 scikit-learn objects, estimator and hyperparameter optimization, like a random search CV. And one thing that's important, this is, so how it will select the best combination of hyperparameter. It will do like a cross-validation to test and to assess it. And the cross-validation with the higher F1 score, macro average F1 score, it will be selected. So for example, you can optimize for several metrics. Scikit-learn has support for everything, and Landmapper is compatible with all of these metrics. And basically you can start run it now. And in this case, so while it's running, I will explain. So points are my samples. Feature, column, prefix, it's basically because I have like a data frame with multiple columns, but only a few of these columns will be used by the model. And I'm using like a prefix rule to select what are the columns that I need to use. So LCV, it's basically the columns that refers to the Landsat, to what we did, the overlay. But you could also provide, I don't know, I think it's feature calls, and just provide like the full name of all the columns. The target call, it's basically what we want to train the model. So it's the classification class. So 1 or 2, others for pasture. Estimator, it's the random forest, but you could have another estimator compatible with scikit-learn. The hyperparameter selection, it's the object used to do the hyperparameter tuning. The CV, it's just 5. You could have different cross-validation strategies, but here it's just 5-fold cross-validation. Minimal samples per class, it's just a way to, for example, remove samples with really like a small coverage in the sample. So for example, you can remove all the samples that has less than 1%. We set 0 here. It's just because we want to use all the samples. It doesn't matter this rule. And I set the variables just to follow the progress. So here we can see that the first thing, because some algorithms, they doesn't work with class starting from 1. So for example, XGBoost, I tested and it didn't work. So basically, the first thing is do a transformation of the class to 0 and 1. So considering the input value, it will occur in any way. And here we can see all the 10 combinations tested. So we can see the performance of all the 10 combinations. And the best one, it was 0.61. And here are the parameters that were selected. So basically, this is our best model, considering the hyperparameter optimization. And okay, after that, we trained a random forest using this parameter. Again, it's just working with random forest. We trained a random forest and we calculated the evaluation metrics considering also the spatial cross-validation. So it means that it used a spatial cross-validation to select the algorithm. And for all this combination, it trained a new random forest. So we had 10 random forests here. But after the selection of the best parameter, it trains another random forest now using these parameters to just predict the samples using the spatial, not using the cross-validation strategy. And the method that is used, basically like under the hood, it's this one, cross-val predict. What this method does, it's just a way to predict your samples. It predicts, it generates like a prediction that it's valid considering all the folds of the 5-fold spatial cross-validation. So basically, for example, if you have a 5-fold spatial cross-validation like this, so it will fit one model per each fold, and for this fold here, it will remove and train one model with this remain data. But as we removed this fold one, you can use the trained model to do the prediction. So we have a valid predicted value for all the folds. And if you sum up everything, you can have like a valid prediction result. So a predicted value using 5 models, considering this fold strategy, and the expected value. And with that, you can calculate any kind of metric that you want. You can generate a confusion matrix, it's valid, because you are not training and validating the same samples. That would not work, or it would work, but it would be a clear sign of overfitting. So Landmapper did everything, but the last step is we just use this cross-validation strategy to select, to calculate the assessment metrics. So because in the end, if we select one of these models, the model will not, for example, use all the training data. It will use just 80%. So the last step, it's actually train one model using all the samples. So the whole workflow here, trained 10 models to do the selection of the hyperparameters, trained five models to do actually it's more than 10 models. It's 10 multiplied by 5, it's 50 models. 5 models to do the evaluation metrics, and 1 model to actually do the prediction. So the final model with all the samples, with the best parameters, that's the one that we use to do the prediction. And here we have a evaluation report. So this is what we have considering precision, recall, F1 score, so several metrics. And the macro average, in this case, it's 62. Okay, but you are free to derive any kind of metric because, again, we have the expected value and the predicted value. And this predicted value is completely valid. So you can use it to derive confusion matrix and additional metrics because it was derived out of the fold. Okay, so what we will do now to do the prediction, it's basically we will use the leaflet. I tried to add a cloud optimized geotiff here, but I didn't manage to work. I know that there are some packages, but it didn't work. So what I will do, I will use the IPy leaflet to zoom in an area where I know that might have some pasture in Scotland. And I basically will draw like a geometry here. Okay, so you can do it in any place of Europe because we have data for any place in Europe. And so considering this region, it will retrieve the bounds. So this is actually the bounds, the extent of the area that I selected. It works just with the first area. So if you need to select another area, I don't know if you need to rerun the cell, but maybe it will just get the, yes, it will get just the last one. Okay, after that, what is happening here, considering the bounding box, as I mentioned, this bounding box, it's also in the APSG 4326. So we need to convert it to the projection system of the raster data, because we will use this bounding box just to retrieve a very specific region of the raster data. And so we have the window here, definition, and this window, it's just an object from the raster IO. But as it is a space-time prediction, we have a small problem here. So the Landmapper is expecting these column names, these feature names, these covariates without the year. And the raster data that we have, it's actually located in time. So we have the name, the year in the name. So the only way that I found to manage it, it's actually ask to the users to provide like a map to really associate what and explicitly remove it to match it. So there is a parameter called dict layer new names that you need to provide to actually do space-time prediction. But for example, if you want to predict a different year, it's the same thing. So you just remove, for example, 2000, and you will end up with this expected value. So it's basically a way to map and say to the Landmapper that the actual feature that the model is expecting is provided by a different name here. And doing it, you can call the Landmapper predict. So basically here, it's reading the URLs. This is a remote file, but it's sending like the window. The window is the window defined in the IPy leaflet. So what is happening here for these 4 rasters that we are providing as input, it's retrieving just that portion of data. So this is, again, it's possible just because of that random access provided by the HTTP request. It's matching the name, and it's explained that the output should be a EUMAP pasture classification file, .diff. So it took 5 seconds to do the prediction, but this is just the random forest time, not the time to really access the data. To access the data took more. So of course, if you select like a huge area, I don't know, a whole country, for sure in Colab it will not work, but it might crash because you need to retrieve so many data remotely, and maybe the network could be a bottleneck here. You can use this class, this helper function plotter, to actually see the result. So we produce it like a classification map here, but this is not really helpful. So what I will do, I will just download it and open the QuantGIS. So this is the output of our model. like a random forest that we implemented and a hyperparameter optimization. So I will open the file. Okay. Now zoom in. But so the predicted value here, it's kind of the opposite. So 0, it's pasture, and 1, it's others. So if you want to really see just you need to change the style. So I will do it. I will just put 0 here and put like a color. No, this. Okay. And I will say that actually the node data here is 1. So basically, this is a very simple model, produced with like really small set of samples, but just to illustrate the workflow. So what we are seeing here is what the model is calling pasture. And of course, it's removing all the forest and things like that. So, and it's just using 4 bands, SWOR 1, 4 images from 2020. And okay. So yeah, basically here I'm providing a few additional information. So what we did, it's what we are calling space-time overlay, but again, you can do a space overlay. Just take your samples, use the same approach, but without informing the date and matching all the names. And you can do like a point overlay. So here there is like a tutorial that you can use to implement the space-time overlay. So it doesn't matter the time here. So if you have, I don't know, multiple points as soil samples, if you have multiple points in the same coordinate, they will have the same value, but it's a kind of effect of your data set. Other thing is, we are also, as I mentioned, we have full compatibility with the scikit-learn. So this is a very simple way to classify. It's one classifier, just hard class, but you can derive, for example, probabilities. And if you just use the Landmapper saying that, okay, I want to use the predict method and predict probabilities, it will produce actually 2 files, 0 and 1, and you can use it to really analyze the probabilities derived from the algorithm. Here we are also providing like examples of feature selection and ensemble machine learning, so combining multiple algorithms and things like that. And other, there is also like a more comprehensive tutorial about the stack. So here it's like explanation how we actually create our stack. So we had a kind of Google Drive spreadsheet with all the metadata, and we used it to populate the stack and create all the JSON files. And here it's also like a few more examples of how you can actually interact with the stack. So we have this like helper function to plot, for example, all the thumbnails and see like an integrated view of the time series. And here we didn't access the data directly, but the Landmapper accessed it. But for example, in this tutorial, it's presented how to read the data remotely. So you just send the URL and the window defined with the IPyLiftLab, and you just have the data. So you have the data as a NumPy array ready to go. And if you want to save it locally, so you can use it to actually access the stack and, I don't know, crop or clip 100 layers and just save it locally. And to save, we also have like a method called save rasters. And you just send like, what are the rasters that you want to, what is the output file? There's a documentation describing it. What is the data, but you need to provide like one base raster. And it will, for example, use all the properties of this base raster. So pixel size, projection system, everything. It will use it and save it locally. And of course, as we are dealing with big mosaics, you need to remember to pass the window. So it will do everything just for that small area that you defined. And lastly, there is also this tutorial that explains how to use these three libraries: Bottleneck, NumPy, Expert, I don't know if it's the right way to say, and Numba. So basically here, it's also accessing cloud optimized GeoTIFF and doing like some NumPy computation and implementing a benchmark. So there's like some results here to implement array reduction and see, for example, what of these libraries have like are more like fast to access and do, for example, average and things like that. And I also add like a last kind of exercise that you could try to update the workflow to add more covariates, not too much. It will not work probably with 100, but you can add, for example, one more to see if the result improves. And you can also try to predict probabilities using what is explained in the tutorial of the EU method. And yeah, that's all. And I'm open for questions.
So for those of you doing the hackathon, Leandro already did it for you now.
Yes.
You just have to find the code. And now this is just the Europe, right? So
Yes, because
if you want to do the whole world, then it's better to use the matrix.
So I have a question about this space-time overlay. How do you do the time matching? Is that a time of an observation? You typically don't have a scene, right? How do you match that?
yeah, basically here we are doing it for the file name. So we are assuming that to work with that, you need to have like a few time reference in some time reference in the name, but here it's just the year. So this is one way, mostly this is what we do mostly, but in the official tutorial, we also have like a different data set organized by year. So you can have like a folder, and inside of each folder, you can have 2000, 2001, 2002. And inside of this folder, you can have like the variable name. And the variable name is basically the TIFF name.
So it's already an aggregation for a full year.
Yes.
Okay.
So you can work with a predefined file structure, that folder structure, or you can work with this on-the-fly replace for URLs.
Yeah.
Any more questions?
Maybe,
Yep, no, go ahead.
maybe in your experience with this kind of data, specifically for pastures, which are the algorithms? I know from previous that Professor Tom said before that machine learning ensembles are the better. But for example, do you have a rule of thumb about which algorithms you run first, like random forest or not neural networks, either support vector machines, but there is kind of rule of thumb to where to start, specifically in the modeling part?
Yes. So yeah, random forest, of course, it's the first option because it works out of the box. I also test, for example, the gradient descendant tree implemented by XGBoost. But the problem is you need to have like a high hyperparameter optimization, otherwise the results will not work. So it's kind of mandatory have a hyperparameter optimization for the XGBoost algorithms. Surprisingly, I'm using also like a regular and pretty simple artificial neural network, like a really 4 layers and several hidden neurons. So it's pretty simple, and I'm using through this Keras classifier. It's basically a wrapper for TensorFlow. So it's a way to integrate the TensorFlow in all the functionalities that you have for the scikit-learn. So you can do hyperparameter optimization and things like that. And as the Landmapper is compatible with the scikit-learn interface, you can use it internally. I also tested a bit the supported vector machine, but it's pretty slow. So I always heard that, okay, it's a nice algorithm and you can use, but I think it doesn't scale up more than 5,000 samples. It's 10,000 most. But surprisingly, it's also, the implementation is a scikit-learn, it's also slow to do prediction. So, and there is something related with the kernel that you need to define. I tested once, like use the support vector machine in the same way that random forest works. So you could have like instead trees, multiple support vector machines and like working as an ensemble. So it helps a bit to scale up, but it's really tricky and didn't improve too much the accuracy. And yeah, for the ensemble, we have like an example in this tutorial, but it's important. Don't always explain also about it. So it's important to have like algorithms that are comparable in accuracy. Otherwise, you are just putting an algorithm that will be disregarded in the end of the prediction. But also like not only tree based. So for example, if you have random forest and XGBoost working with the trees, it's 2 algorithms that are tree based. So you need to have like a kind of other algorithm to improve the performance and the generalization. And that's where we are using the artificial neural network, like a fully connected artificial neural.
Thank you. And I have another question, and it is about the spectral indices. But I would like maybe just to check out really detailed.
Okay. Yeah, we also use the spectral indices. Sometimes it's general, the approach that we implement in internet, we overlay with the maximum number of coverts available. So maybe, I don't know, 500. And later we do a feature selection. So we objectively select what are the best variables. And sometimes just like NDVI pop up and it's better than, I don't know, green band. So, but we have like a kind of set of spectral indices that we always calculate, and like NDVI, EVI.
But they are calculated before, for example, in another software, right? Or not directly?
You can calculate, like, for example, in the data table. So imagine you have the green, the red, and the near. So you can calculate and derive, generate a new column. So this is the NDVI. And you can also calculate on the fly in the UMap. It's more tricky, and the interface, it's not good, but it's a way to not really generate all the spectral indices like physically as image to save, and just generate on the fly during the prediction.
During the cross-validations, you might have the 5 or 10 models, and for the prediction, you use the 1 model. I would like to know that each model is selected for the kind of prediction. The best one is
Yes, so the cross-validation in the way that it's implemented here. So basically, we are testing like a kind of random combination of hyperparameter. And in this case, we offered for the UMap like a evaluation metric. So this is the macro average of the F1 score calculated with cross-validation. So you can actually compare all these combinations of parameter to select what is the best parameter to optimize the metric that you provided. So in this case, it's just like a way, and you need to refit and train multiple models to do it properly, but it's just a way to find the best parameters. And with these best parameters, you train a new model. So it could be high computational. So for example, if you provide like I don't know, artificial neural network here, it will train multiple artificial neural networks and things like that. So, but this is just for the hyperparameter optimization. So if you don't want to implement it, for the random forest, maybe in some cases it's not really necessary. You can just skip this parameter and it will train without this hyperparameter optimization. It's just train one single model and do the prediction.
That means that after the training, run the model for the whole training data.
Yes, the assumption here is because there is no way to find the best parameter using all the training data, because otherwise it will be overfitted, right? So if you use all the samples and you do the assessment, it's not valid. So every time that you do a cross-validation, you need to like really separate and have a separated fold of your training data. So you never use all the training data to do any kind of hyperparameter optimization or any kind of cross-validation. So because implicitly you always need to remove, otherwise it will be not valid. So in the end, we train one model using all the samples. And the assumption here is everything that you did, because here you are doing multiple models, it's multiple refits and things like that. Everything that you did, it's valid for a bigger training data. So in essence, everything that you did till here uses 80% of the data. So if you use 100%, probably, like really likely, it will not drop your accuracy. It will increase because you are providing a bit more data and more ways to teach the model. Okay.
We have to stop.
Yes.
Okay, thank you so much.
Thank you.
If you forgot